welcome back. In this lecture, I'm going to discuss about how do we solve very simple surface integrals. So, a surface integral is denoted here by this symbol. Let's first discuss about what is the meaning of this symbol. So here f is a vector field, and I'm going to consider f is a vector field in three-dimensional space. It has three components, and S is a surface. Okay, so f dot ds. So ds is a vector element. So f dot ds of that integral denotes the flux of the vector field out of the surface. So we are going to consider that S is an oriented surface, and oriented surface meaning that you have to have a direction of the surface. Normally, if you have a closed surface, then outward direction is the orientation. Otherwise, we will denote a direction of the surface, which is solve f dot ds for f equals y comma x comma z, where S consists of, I will say S consists of z equals 1 minus x square minus y square in a unit disk. Okay, that's all information we need to know. So let's first interpret what is this S. So S has two parts. One part is z equals 1 minus x square minus y square, which is a paraboloid going down. The vertex of the paraboloid is at z equal to 1, and it is going down. It intersects at z equal to 0. The intersection of the paraboloid at z equal to 0 is the unit disk x square plus y square less than or equal to 1. So we can say that this is a volume bounded by the paraboloid and z equal to 0 surface or xy plane. So sometimes we can restate this surface. So it's a solid body bounded by the paraboloid and xy plane, and the surface or boundary of the solid body is this surface. To understand in a better way, perhaps look at the surface that it consists of two parts. One part is the paraboloid, one part is the jet. Okay. So the idea is we will start with this vector integral, and here f is a vector, s is a vector. So I'm just for simplicity not using the arrow sign. Let's assume that f is boldface, s is boldface, the vector. So we want to convert this vector field, this vector integration into a scalar integration, where f is still a vector field, but now earlier the vector field was a function of x, y, z. So now I'm going to consider two parameters, u and v. So the vector field will be a function of two parameters u and v, and with a dot product of the normal from this vector, which is denoted by Ru cross Rp. Okay, so today I'm not going to discuss about how to derive this conversion or the parameterization. That is in other lecture I have discussed. So that is what we know. Let's assume for today is that we know the surface integral is converted into this simple scalar double integral. Okay, this quantity is a scalar dot product, gives you a scalar field. Okay, so how we are going to parameterize this vector field. So the idea is I start with a position vector r, which is x, y, z, and then I think of that x is dependent on two parameters u and v. The y coordinate is also dependent on two parameters u and v, and z coordinate is dependent on two parameters u and v, and that can be uh, expressed in multiple ways. One person will come with one type of parameterization. So if I'm looking at here, I'm going to think maybe this one is a kind of a polar coordinate type things. So I can think of considering some polar coordinate, and maybe we can write polar coordinate r and theta instead of u and v, but instead of doing that, I'm still using the same symbol u and v. So let's think of that. If I have to consider x like a polar coordinate, so r cos theta, maybe if I think of u for r, so I will say u cos v, okay, r cos theta or u cos v. So y will be, this is y will be u sin v. Okay. Now z has to be come up with one of the given equation for the surface. So the equation here is the paraboloid. If I look at here, I can say z equals 1 minus x square plus y square. Now you look at here, x square plus y square gives you u square cos square v plus u square sin square v, which becomes just u square. So that will be simply 1 minus u square. As a side note, maybe we can think of say if we use standard polar coordinate symbol, that is not a bad idea to write r theta. The only problem is that my position vector symbol is r and polar coordinate radius is r. That's okay. So we could change that symbol, and that would be r cos theta, r sin theta, and 1 minus r square. So we can perhaps change this r to something, maybe say gamma. So it does not matter which symbol we use, we just have to think of considering converting the integral in terms of two parameters. Okay, so now let's continue working on this. As long as we have found this parameterization, that would be the first objective, and after that everything is straightforward, just simple algebra. So what I will do is that I will first I want to find this ru cross rv. So I will differentiate r with respect to u, so that's a partial derivative. So it will be cos v sin v negative 2u, right? So you differentiate with respect to u. Now you differentiate this with respect to v. So once you differentiate with respect to v, you get u which stays constant, sin v u cos v, and third component 0. Okay. So now you take ru cross rv. So ru is a vector, rv, r sub v is a vector. So you take the cross product, and you can look at here. It's written conveniently like a determinant. So you can just think of I hat, j hat, k hat, and you can calculate the cross product. So the cross product will be, you can also cross check in your way of calculation of cross product, but that's straightforward. 2u square cos v, and then we look at the middle term where we have a minus sign, so we change the order of the calculation of the cofactor. So we have again 2u square cos v, and then the third term will be, if we just look at here, u cos square v minus plus u sin square v. So you can take u out, you get u times sin square v plus cos square v, which is 1. Okay, so then we solve this integral here. So let's write down first the vector field. So look at the here, the vector field is y comma x comma z. So y, which is u sin v comma x, so u cos v, and z is 1 minus u square. Okay, and take the dot product with ru cross rv, which is ru square cos v comma 2u square, so 2u square cos v comma 2u square cos v. I think I have a sin v. Yeah, the second one is sin v. Yeah, sorry about that. So here is a sin. Okay, here is a sin. That's okay. And the third term is u. So you can write du dv, or this part is maybe you can write dA. So the d is here a disk, but then we can also figure out the limit for the disk here. So let's do a back of the envelope calculation. So the disk is coming from here, and in polar coordinate type parameterization. So v will be the whole circle, and u will be just up to the disk. So the limit will be for u from 0 to 1, and for v from 0 to 2 pi. Okay, so that sometimes gives a pain of understanding the limit. So just simply look at here, u cos v. So v is an angle, so its limit is going from 0 to 2 pi. So whether you go for 0 to 2 pi or a part of that, it depends on the given surface. So the bottom part of the surface is x square plus y square less than or equal to 1, which tells you that that is a unit disk centered at origin. So if you have a centered at origin unit disk, you have a full circle. So then you go for 0 to 2 pi. And since this is a unit disk, u looks like the amplitude or radius of the disk. So that is u is going from 0 to 1. Okay, so we can now put the limit here. So let's put v limit outside. So 0 to 2 pi, u limit inside 0 to 1, and then complete the dot product. So it will be 2u cube sine v cos v plus middle term 2u cube sine v cos v, and then you're getting u times 1 minus u square, so u minus u square. Maybe put a bracket here, and inner integral is u, outer integral is with respect to v. So you can see these two terms come up like 4u cube sine v cos b, and I'm going to integrate with respect to u. So 4u cube, antiderivative of 4u cube will be just u to the power 4 sine v cos v stays as is. And then the last time we have u minus, I believe that is u cube there. So u minus u cube. So you take antiderivative of u minus u cube. So you get 1/2 u square minus 1/4 u cube. And then set the limit from 0 to 1. And then write down or carry forward the integration with respect to b. Okay, let's just focus on the inner integral. So maybe the good idea would be inner integral, you set the limit. So if you put the limit, you get sine v cos b here. Maybe I can put a half, so then it will be 2 sine v cos b, so sine 2v, and u to the power 4, you put u equal to 1 plus half u square, half minus 1/4. So everything integrated from 0 to 2 pi with respect to dv. So this half minus 1/4 will be just 1/4. And you can think of that this is an integration of sine 2b from 0 to 2 pi. So that might be 0 is because of just if you think of the calculus minus a to plus a fx dx, and if fx change sign, fx is even a function of order function what happened, but it does not hurt for you to just simply calculate that. So let's keep half. The integration will be negative half cos of 2b 0 to 2 pi, and that part plus 1/4 stays here, v 0 to 2 pi. So obviously here you get minus 1/4 out, and cos 2b, you set b for 2 pi, cos 4 pi. So cos 2 pi, cos 4 pi is 1, minus cos 0, which is also 1. So 1/4 to pi. So that comes up with pi over 2. So I hope this is clear. Let's go back and review the process. The presentation dependent on how do we solve double integrals, that's a prerequisite knowledge, and how do we parameterize. So I'm going to assume here is that parameterization is already known, or I have given the previous lecture, and how to solve double integral maybe we have learned already before coming to this lecture. And if that we have already learned also that a surface integral of a vector field is converted to a double integral with respect to by using some sort of parameterization. So as long as we know that, we see that we can solve this flux problem. So here, just to test ourselves, so I'm going to give you an exercise. So in this exercise, so I'm going to say consider a surface S that is half of the sphere. The sphere, which is x squared plus y squared plus z squared equals 1. Okay. Such that z is greater than or equal to 0, or I could say upper half of the sphere, but more specifically z is greater than or equal to 0. So z coordinate I'm going to assume the particle coordinate. Okay, so then a vector field E is given by z comma yz comma 2x. Okay, find the outward flux. E dot ds. That's enough statement. You can say outer flux through S, but doesn't matter. So the surface is given by this time is given by half of the sphere. See, this time I did not mention here surface consists of a part of the sphere and the disk, rather than the statement should be clear. The surface S is half of the sphere such that z is greater than or equal to 0. So the sphere is just outside shell where z is greater than or equal to 0. If you cut a sphere, you can put a disk to close the sphere. Once you cut a sphere, it's empty. Inside is empty. It is just a shell. Okay. So but the previous example, the example I have done, where I said I have a paraboloid above z equal to 0, very similar to half sphere. The paraboloid above z equal to 0, but I said the surface consists of the paraboloid and the disk. So that is a closed surface. And this one, the surface is just half of the sphere. So disk is not included. So you have to be careful about that. So think about how do you solve and then follow the same procedure. If you have any question, you can just email me if you don't understand, or if you want to verify your solution, you can also contact me. Thank you very much.